There you are, my little linear algebra babies. You're back. So, part B, section 3, chapter 4, we're still talking about basis vectors and the idea of linear independence as applied to a general vector space. So when we left off last video, I said that there are two vectors in R2, right? That are very important basis vectors, and there are two vectors that I would be surprised if you have not seen them before. And those two vectors are what we call the I vector, J vector, and to make sure, just in case you haven't had any exposure to physics, each the I vector, J vector, these are unit vectors, right? Meaning unit vectors that they have a magnitude of 1. And they are the I, or the direction, I should say, the direction of the I vector is heading in towards the positive x-axis, and the direction of the J vector is heading in the direction of the positive y-axis. So really, just to make sure you understand, because they have a magnitude of 1, right? Because they have a magnitude of 1, it's the direction of these vectors that make them so important, and as well as the fact that they are separated by 90 degrees. So I want to make sure you understand that I know that you've been plotting points in your XY coordinate system ever since probably elementary school, right? So if I gave you the point 3, 2, you would go over 3 up 2. Now let me make sure I can go over 3 up 2. Here would be your point 3, 2. Of course, since this is linear algebra, we are referring to this as vector 3, 2, but same idea. Now, what I want you to understand is that when you have when you're thinking about basis vectors, the idea is that basis vectors will span all of well, in this case R2, the entirety of the space that you're in. So let me kind of give you an example. So I've already graphed this vector v, right? So we have to assume that somebody comes along and gives you vector v, and what I'm trying to tell you is that from I and j, just with these two vectors and obviously some scalars, I can get to the point 3, 2, right? I can get to the point 3, 2 from the linear combination of these two vectors. So let's make sure you understand. So remember, it's c sub 1, and in this case, the I vector is 1, 0, plus c sub 2, and the j vector is 0, 1. So it doesn't take very long for you to figure out that the scalars that you should choose are in fact the x and y value of the point, right? So the point 3, 2 really, truly means you have a weight of 3 attached to your I vector and a weight of 2 attached to your j vector. And from the choice of those two weights, you can get to the vector 3, 2. And it goes without saying that I can get to any vector, any point in R2, just by choosing different weights attached to I and j. So I and j are extremely important but they're not important because of what I just did there. They're not important because they allow me to get to any point in space. In fact, any two vectors, okay, now there are a few assumptions, right? As long as you're not dealing with the zero vector, and as long as they're not multiples of each other, but any two vectors can get you to any other vector in the same space, just by doing linear combinations. The reason why I and j are so prevalent and so important is, well, one, because they have a magnitude of 1, and 2, because you have that nice 90 degrees of separation, which let's see, if I just randomly chose two other vectors in here, you would start to see some you would be graphing with very odd looking coordinate systems, right? So you might, depending on the vectors that I chose to build for the bases, you might be plotting points that look, and I'm not lying, the graph paper might look something like this. So that 90 degrees of separation, and along with the fact that they are unit vectors, and makes just works out perfectly when we start thinking about plotting points. So these are two basis vectors. Now, what I want to do is, so we're going to talk a little bit more about basis vectors, or at least a lot more in the next section. But your only takeaway right now is, look, when you have basis vectors, and you can use your basis vectors to get to any other vector in that space. So how does this play a role in what we're doing right now? Well, obviously we've been talking a lot about spaces and subspaces, right? And now in this case, let's talk a little bit about subspaces. So H is a subspace. Now I'm gonna give you some in other words down here at the bottom in just a second. But so if H is a subspace of a vector space V, right? Now, if you have a set of vectors, like we had I and J, but you don't have to have just two. But if you have a set of vectors in V that serves as a basis for subspace H, right? That's the idea. So we have an indexed set of vectors, meaning B sub 1, B sub 2, B sub 3. NV is a basis for H if, well, let's read each one and then do it in other words. If B is meaning your set is a linearly independent set. Okay, and all that means is they're not multiples of each other. Okay, I and J are not scalar multiples. You cannot build one from the other by choosing a scalar. So they can't be scalar multiples of each other. And two, the subspace spanned by that set of vectors B has to coincide with H. And what that really means, so this what they're trying to say here is, look, when you take the span of your base vectors, you better be able to reach every single point in your subspace. Otherwise, you don't have a basis, right? So the set of vectors, right? This is your set of vectors, must truly span all of your subspace H. You got to be able to get to every point in H from just using that set of vectors. Otherwise, they're not basis vectors. So, example 7. Let's do an example. So we're given 3 vectors, and we are told that your subspace H, right? So imagine that some region is equal to the span of those three vectors. Now, I do hope that this is not getting too much for you. Remember, the span is just the linear combination of the vectors. And what they're really saying here is, look, from that linear combination, you can reach every single point in your subspace H. All right, now, so that aside, it says, note that V sub 3, that meaning this vector right here, can actually be built from the other two vectors. Okay, so that means you do have multiples, right? Maybe, let me see if this helps you, and maybe this will help you visualize what I'm trying to say. So here, right here is all of three-dimensional space, right? X, Y, Z. So here's every single point in three-dimensional space. Now, if I give you just two vectors in that space, right? Let's assume that I only give you two vectors. You're not, remember, you have to have three vectors to get to span all of three-dimensional space. If you only have two vectors, that would be like, you can think of it like you can only span just a plane, right? Just imagine a piece of paper cutting through this three-dimensional space region. So do you understand that with just two vectors, you can span a plane, but you can't span all of three-dimensional space. So what you need is a third vector, right? And I'm actually going to write this third vector in a different color because I'm going to make sure you understand what this is saying. So you definitely need a third vector to span all of R3. But here you go. Wait a minute. What if I say, okay, no problem. I'll give you another vector. But then I reach into this shaded region, this plane, and I pick a vector from there. Does that help you reach the rest of space? No, you can't pick another vector that's already in the span of the first two vectors. Right now, if instead I were to choose a vector that's not in the span of those first two vectors, all right, then that would be helpful. That would help me reach the rest of R3. So really I hope that's, in other words, is helping you understand what's really happening here. So when they say that V sub 3 can be built from the other two vectors, that's the equivalent of saying, look, this V sub 3 is just some vector that's in the span of the first two vectors. Okay, it's not helping you out at all. So we want to show that the span of those three vectors is the equivalent to the span of the first two vectors. In other words, right? I don't know how many times I can say in other words, but in other words, this vector right here is just garbage. It's contributing nothing to, it's contributing no help. How's that? So we could actually throw this out and we would still have the same region of the shaded region as we would have when we started. All right. So that's what's happening here. Now, let me go ahead and start with. Let me go ahead and actually start by answering this question because we want to. That's like intuitively that is what's happening. I am going to be able to throw out that third vector, but that's me just talking about it is not showing you. It's not showing it. So let me give myself a little bit of space here. Let me show you how you can actually prove that third vector contributes nothing to the span. So ready? Let's start with the idea that you have. We started with three vectors: c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3. And we are supposed to show that that's the equivalent of c sub 1. I'm going to give myself a little bit more space here. We're supposed to show that the span of those three vectors is equal to just the span of the first two vectors. Okay, and how do we do that? Well, so I've written the span of the first three vectors, and now I'm going to set that equal to the span of the first two vectors. So c sub 2, c sub 1 v sub 1 plus c sub 2 v sub 2. So somehow these are supposed to be equal. Okay. All right, so in this case, you can think of it as I'm trying to think of the best way to, because I don't want to stay here in theory too long. Well, let's think of it like this. So the first, looking at just the right side, right? I'm just gonna kind of take a look at this. Because we are already told that v sub 3 could be built from the linear combinations of v sub 1 and v sub 2, then I can just think about, I can add that third vector v sub 3. Only the weight of that vector would be 0. Right? So that's what we mean by the fact that you can build it from the other two vectors. The fact that the v sub 3 is in the span of v sub 1 and v sub 2 is basically thinking about having a weight of 0 attached to v sub 3. So if c sub 3 is equal to 0, and I plug 0 in here, if 0 is equal to v sub 3, then that would mean that c sub 3 has to equal 0 here. So if I plug a 0 in for c sub 3, what am I left with? I'm just simply left with exactly what we were told. C sub 1 plus times v sub 1 plus c sub 2 times v sub 2 is equal to c sub 1 times v sub 1 plus c sub 2 times v sub 2. These zero out now that I know that c sub 3 has to equal 0. So, okay. Now, the second part to that question is, well, let me give myself a little bit of space here. The second part to that question, and I'm going to scroll back, is then find the basis for subspace H. So that's what I'm going to try to tackle right now. So the basis for the subspace H. All right. Are you with me? Are you still along for this ride? So what does it mean to have the basis for a subspace H? All right, well, there's a set of vectors out there, right, that from those two vectors, they would form a basis for H if they allow me to reach every single point in subspace H. All right, so how are we going to do this? So let's just, now I don't know what H looks like because they don't define, well, they do define it as the span, I'm sorry. But let's just assume that, to make this work, let's assume that X is some vector, some point that's actually in subspace H. Okay. So what I'm going to do is, since I'm trying to find a basis, right? I'm trying to show what the basis would be for H. I'm going to take X and set it equal to c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3. Okay, so I can reach any point in H by just choosing some various scalars to multiply by these vectors. Now, the caveat here is right there in example 7, it says v sub 3 is equal to 5 v sub 1 plus 3 v sub 2. So how am I going to find a basis? Here's what I'm about to do. I'm about to plug that little caveat in for v sub 3. Ready? Let's go ahead and write what that looks like. So now I have x is equal to c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3. And now that's going to be multiplied by 5 v sub 1 plus 3 v sub 2. With me so far? Maybe, right? Potentially. All right, I'm going to distribute the c sub 3. So let's write that. Almost there. So x is equal to c sub 1 times v sub 1 plus c sub 2 times v sub 2. Ready? Plus, let's write that as, I'm just going to write that as c sub 3 times 5 v sub 1 plus c sub 3 times 3 v sub 2. And here's what's going to happen. First off, do you notice that the only thing left in our linear combination is the two vectors, v1 and v2? So I'm going to do two steps at once. I'm going to group all of the v sub 1s, okay, beside each other, and all the v sub 2s beside each other, and then I'm going to factor out a v sub 1 and a v sub 2. Ready? So that gets me to x is equal to, if I factor out a v sub 1, actually let me write it this way. So if I factor out a v sub 1, what would be left is c sub 1 plus 5 c sub 3 times v sub 1 plus, and now I got c sub 2 plus 3 c sub 3 times v sub 2. Okay, so at this stage of the game, we start to forget what we're even trying to do. And what we were trying to do is find a basis where I can reach any point in the subspace of H. And what we're showing right now is, will you agree with me? Will you grant me that c sub 1 plus 5 c sub 2, I don't know what that's going to equal, but it's just going to be a scalar, right? In other words, you just simply have, I'm going to write a capital C with no subscript. In other words, x is going to be just a scalar multiplied by v sub 1, right? Plus, now I'm going to use, instead of using c, I'm going to use k. If you take a scalar and then add it to 3 times another scalar, you're still left with a scalar attached to v sub 2. So in that scenario, what is the span? What is the answer to this question? The span, or any vector x, is in the span of these two basis vectors. It's just v1 and v2. All right. So the theorem that you see below is just the more formal way of me telling you that sometimes you can throw out a vector if it's not if the third vector is in the span of the first two vectors, then it is not contributing anything. Okay. And the last bit of material for this section, and instead of doing this in a, if you need to take a break, you take a break, okay? But the last bit of material for this section is to answer the question about the basis the bases of a null space and a column space. All right, so I want to know what the basis vectors would look like for those two spaces. All right, here we go. I got my two boys. I think they're play fighting in the background, so it's very possible that if one of them starts crying, I might have to stop this video right smack in the middle of it and go make sure they're okay. But I think so far I think they're okay. So let's go ahead and answer example 8. So we are asked to find a basis for, do you remember this? This is the column space of B. Now, what is B? Well, here is matrix B right here. All right, this is B. The column, so find the basis for a column space. All right, let's do this. So it's actually very easy to find a basis for a column space. Very, very easy. So if you had to pick which, inside B, which ones are the, which columns are going to represent the free variables? I'll give you a second to think about that. So, do you agree with me that this column right here is representing a free variable? These are non-pivot columns. And so is this guy right here. You see how that's also a non-pivot column? It's just it's the free variable. Guess what? Those columns, now remember, each column is a vector, okay? Those are the ones that you can throw out and when you're dealing with a column space. So you go ahead, you take a matrix, you row reduce your matrix, and then you take any of your columns that are the free variable columns, and then you toss those out. Those are not needed. So let's label. So this is B sub 1, B sub 2, B sub 3, B sub 4, B sub 5. Now, aside from the ones that I've highlighted, every other column has a pivot in it. In other words, it has a basic variable. So I need those in my basis. I don't need the columns with the free variables. So what is the basis? Quite simply, it's B sub 1, B sub 3, and B sub 5. With those three vectors, I can reach all of the column space. Those four serve as a basis. All right. Now, I hope that makes sense about the free variables because, look, I mean, B sub 2 is equal to 4 B sub 1, right? I mean, these multiples contribute nothing to the span here. So, all right. Let me see if there's anything else I want to tell you. Bear with me here. Okay, so I'm not going to answer the question about how do you find the basis for a null space, because I think I will do that in the next video. But it's actually, we've already learned the technique. It's the same, the basis for a null space. It's pretty easy. We just do the same techniques that we did in 4.2. But I will do one of those in the next section when we're talking about a more in-depth look at basis vectors. Until then, you guys stay safe.